Yeah, okay. Neutral atom, you can, yes. Okay, so let's revisit one more time. Every time you see a new quantum computing architecture, you ask this question. Does it have a well-characterized 2-qubit? Can you initialize it easily? Does it have a long decoherence time? Do you have a universal set of quantum gates? Most importantly, 1-qubit gates plus an entanglement gate. And then can you measure them individually, right? Trap ion can do that. How about photonics? So this paper, you can take a look, pretty good. So usually what they do in encoding in the photonic is so-called dual rail encoding. So it is like use two long overlap, for example, two long overlapping propagation paths. Okay, so instead of saying in this path I have 0 and 1 photon, and then there is a superposition of 0 and 1, it's more like saying the photon is on this path and this path. And there's a superposition of either the photon is on this path and not on the second path. Is that okay? So that is a dual rail. And the good thing about this is that, what is the good thing? It solves a lot of the error problem, error correction problem already. Not the full error correction, yeah. Yeah, I will show you later. Maybe I should show you now. That is like what I mean by dual rail, right? Which I showed you earlier, but I did not draw it, I just copied from this paper. So you shoot a photon, right, to a path, and they are symmetric, and you only have one photon, so you don't know where it will go because symmetric, half-half possibility, and you can change it so one has higher probability. If you don't measure it, it is a superposition on the whether path 0 or path 1. Once you measure it, it must occur in one of the paths, right? So then you collapse the wave function. Is that okay? But this is in the space mode, we can, in our physical space, it's easy to understand dual rail. But it doesn't mean you always need to have space difference. It can be the mode. They are encoded in different orthogonal mode. Okay? Now, just need to recognize this. The difference of photonic qubit from other qubit is that the photons are moving. You cannot stop a light because its mass is 0. It's always moving, right? So that's why you keep seeing paper, they will say, I was able to slow down the photon to 10 meters per second, and then even almost stationary. So that's a big deal. You can go to Nature Science paper by slowing down the photon, using some maybe material, some special treatment. Okay, but remember, it is moving. Unlike the superconducting qubit, it sit there. We shine the laser pulse, then it evolves, sit there, shine laser pulse. That is the gates, right? But now the photons keep moving. It's not like sitting there, you shine a pulse, then it evolves to another state. There's the difference, right? So as a result, how do you get a qubit? Unlike superconducting qubit, trap ion qubit, you put an ion there, then there's a qubit. Here, you need to generate the photon, because once you generate, then it's gone. You will just keep traveling. Of course, you can confine it, and then eventually you get lost or whatever, right? But the difficulty of photon is the generation and detection. How you detect the photon, right? So I'm just telling you based on what I read that is challenging to the engineer in terms of the compared to other technology. Okay. 1 qubit is easy to implement, as you can imagine. 1 qubit is just rotation of the state, right? 2 qubit is very difficult. 2 qubit, do you know why? Because photon, it has very long, this is a good point, a very long coherence time. Photon doesn't interact with anything, almost. 2 photons can go over each other without changing the path. Right? Unless you go to super high energy, you bend the curve, right? The space, bend it, and then it's going to change, right? Even 2 strong lasers pointing each other, they will just go away. They don't interact with each other. And from now, you already see that how you get interaction of 2 qubit. What did we do in the trapped ion? The spin qubit. We put in 2 quantum dots, right? And then we rely their mutual interaction through the magnetic field generated by themselves. How about the superconducting qubit? We have this transmon, have a capacitor coupling, and then let them go through this I swap gates, right? We just tune it by flux so that they change its resonant frequency, so there will be back and forth coupling. Again, when they couple, means they interact. And then how we do it with trapped ion? We just say that we rely it to interact with other through this, one is through the laser pulse, and other is through the lattice vibration. It means that you can couple to lattice vibration. And then in that case, it means you can lose information easily because you can couple to lattice vibration, right? All we're doing is intended, but there are many non-intended process over there. But now the problem is photon, no matter how you do it, it doesn't change, right? So there are many different schemes, which I don't understand well also. I'm not going to discuss it. One is the so-called KLM model scheme, which is named after the inventor of the paper. You can take a look, okay? Yeah.
Are these run room temperature?
Yeah. So in principle, because photon is so robust, you can just run at room temperature. Nothing will happen, okay? So we talk about the encoding already. So the first thing when we talk about is detection. This is also related to measurement. How do you detect a photon? Particularly, we are using the dual rail. We just need to check whether it's in a certain mode. The simplest thing is whether it's on an optical waveguide, right? So we need photon detector. One of the things is called Geiger mode silicon avalanche diode. So what is an avalanche diode? Let me see, do I need to come here? Maybe I do it later. Or maybe I can do it now, right? So it turned out to be very simple. It's just a diode, right? We know very well a diode is like this. It's a PN junction. And then if we forward bias it, let me put it in the log scale, log I, and then voltage. If I forward bias it, it go up exponentially, eventually linear. That's not what we are interested in. We're going to reverse bias it. Then it has a very tiny leakage current. If you do it well, it has almost no leakage current. But if you keep increasing its reverse voltage, eventually you will see something like this. It becomes a breakdown. Yeah, it can be Zener breakdown or whatever, or avalanche breakdown, but it breaks down, right? So for those who don't know this well, we can explain why there's a breakdown. But you assume you know the energy band diagram. If no, it's not a big deal. It's not in the exam, but so this is a diode under reverse bias. So this is the Fermi level of the P region, and this is the Fermi level of the N region. So in the P region, I have a lot of hole. I have no electron. In the N region, I have a lot of electron. I have no hole. Actually, I have, but just exaggerate. Okay? Now, if you look at this energy landscape, the hole, the electron are here, but they cannot contribute to current, right? Because this is negative. Negative bias. This is positively biased. First of all, it's attracted to the positive region, right? And the potential barrier also tell you that it's not going to climb up because it's going to fall down. So there's no current. Same for the hole. Hole is opposite. You want to go down instead, just like the you want to go up instead, just like the bubble, the gas hole in your water. Like you pour the coke, right? And then the carbon dioxide try to bubble up. They won't go down, right? So it's not going to this direction. So there should be no current, ideally, for a reverse bias diode, ideally. But of course, once in a while, you might actually have some thermally generated electron and hole. Each time you generate electron-hole pair. Here you generate electron and hole, right? Then this one see the electric field, then it's going to go here. This one see the electric field, it is going to go here. But this is very low energy, right? This is the purple. I mean, very low current, right? Because you don't have much. However, if you keep increasing the bias, this is going to be very, very steep. This electron gains a lot of energy when it travels across this so-called depletion region. You can imagine that. Just imagine this as a slope, because the slope is indeed an indication of the potential energy. And that is the exact potential energy an electron will see. What will happen if you go through this slope? You keep accelerating, you keep gaining energy, right? You have high potential energy, eventually gain enough kinetic energy, right? Then, at a certain place, it's going to lose the energy and then generates an electron hole pair. And just think in the spatial case, electron is accelerating, then I see an atom, I knock the atom, because you keep accelerating me, right? I just running in this classroom, you keep dragging me, eventually I will just knock off one of you. And then I generate a hole on the chair, and then you fall down, right? And then you get attracted by the electric field. Then you are going to do the same thing with me. And the hole will go to the another direction, right? And then the hole will get accelerated. Eventually, it's going to lose energy because it's going to generate another electron hole pair. And this process keeps repeating, just like the avalanche in the snow hill, right? Then you get a lot of, keep repeating, and then a lot of electron hole pair generated just because of one electron. As long as the gain is enough, this is like a positive feedback. One electron generate one electron hole pair, the electron generate another electron hole pair, the hole generate another electron hole pair. It's a multiplicative effect. Then you see a huge current going down. Is that okay? About this so-called avalanche breakdown. Okay? Now, and that is how we use the so-called Geiger mode. What we do is, you need to have a very clean environment, also low temperature. When it is at low temperature, I don't have this thermal excited electron. So indeed, I don't have any breakdown. And then we wait. Later, maybe a photon comes in. This photon is going to generate one electron hole pair. And then you will trigger this breakdown. So one photon is enough to trigger a lot of electron and hole. Then you see a spike of the current. Okay? So, but this is not just this. Not exactly Geiger mode. I'll talk about that more later. But here, this is something you need to understand. One is the detection efficiency, right? I don't know what I'm writing here. It's saying that like only 65% of the time you can detect it, right? So I think this is wrong. I mean, what it means is that for each photon, you only have 65% to get it right. So if you have 10 photon, then the efficiency, then the detection, what I mean is detection rate, right? It's 1.3% only successful, right? If you have 10 photon coming out, yeah.
So I guess this is because usually these diodes, they have some substrate and the photon just scatter.
Actually, I don't know, but one possibility is that the electron hole pair got trapped, maybe due to impurity, right? And or it got absorbed in the upper layer. Actually, I'm wrong. It got absorbed before it reached the depletion region. So if you absorb at the neutral region, right, then you cannot do avalanche. I think this is the reason. Right? Because you cannot have the depletion region right at where the photon imprints. Actually, it's possible, but in that case, you have a lot of traps that it can make it worse also. Yeah. So the main reason is that it got absorbed in the neutral region, I believe. Okay. Another thing is once you initiate this avalanche, what should you do? You need to stop it because each avalanche means one photon, right? I want to continue to detect the next photon. It's just like you have avalanche on the mountain. How do you stop it? That is called quenching time. You need a special circuit to stop it from avalanching, right? Another thing is, even there's no photon, you might have electron hole pair generated due to the thermally generated electron hole pair when it is hot, right? State of the art may be 100 per second. So you see that is not good, right? Like every 10 millisecond, you have one avalanche event. So it means your gates need to be fast, or all the things need to compute within 10 milliseconds, for example, right? And there are other things, time jitter, just because quantum mechanics, when does the photon arrive? You actually don't know. And also when was it absorbed? That's just like what we discussed. It can absorb here. If it is absorbed here, maybe you don't get a lot of avalanche. Absorb here, you won't. Absorb here, depletion may be the best, okay? And also, how can you resolve how many photons? If I have 2 photons comes in, you also see the same avalanche, right? Because they are not additive, yeah.
So this dark comes what temperature?
That I'm not sure, actually. Yeah, I don't know what temperature is referring to. Yeah? 4 Kelvin?
I think a lot of these run at 4.
Yes, you need to run at 4 Kelvin, that's right. Okay, so let me just repeat. What I have told you is just the so-called avalanche diode, right? It breaks down at avalanche. But in this single photon avalanche diode, the Geiger mode is that you make it actually beyond the breakdown. But this one is like quasi-equilibrium, right? Just a little thing will make it break down, right? It's just like overstress, okay? So how do you do the quenching? This is one example. So for example, at this one bias, reverse bias it. Then when you suddenly have a photon come in, then you cause avalanche, then you have a large current going down. And then because of this, I have this so-called Smith trigger, then I have pulse sending out. Then I know there's a photon. But once you have a large current going in, this one will have a potential drop. This is equal to IRS, right? So once you have maybe negative IRS because we put it ground, then the potential across the photodiode, instead of this point, it will go to this point, where it is not going to have avalanche, right? That is a way to stop it from being avalanche. And then the current will go down, and this part will go up again, and you will be ready to detect another photon. Is this clear?
So there's a sort of a negative feedback built into it.
Yes, negative feedback, yeah, to stop it. And of course, there are many people trying to improve the circuit because you want to have a very fast quenching time. Okay. How do we detect it? Another thing is to use the so-called superconducting nanowire single-photon detector. And this is easy to understand. You just bias the nanowire at critical current. Do you remember when we say a critical current is at which is no longer superconductive, above which it is no longer superconductive, right? So you bias very close to the critical current. And then, of course, to be superconducting, you need to bias it at 1 to 4 Kelvin. So this is like the most important part in photonic computing, that you need to bias at cryogenic temperature. Yeah, they use niobium nitride as the nanowire. The photon will go in, break the Cooper pairs. Once you break the Cooper pairs, then you create the quasi-particles, and then it goes to the normal state. So then there's a potential drop across your nanowire. When it's superconducting, there's no potential drop, right? And that is a way to get to what we want. Is that okay? Yeah.
So I guess you could just, hard to manage, but let's say if you have some fiber channel, you have this photon traveling, you can just put the nanowire on top of that channel, on that conduit, and you know, just couple, so every time the photon passes there,
I don't know how you do it, but the point is, probably not on top, but if it's a point you want to do detection, for example, here, I want to detect whether it is here or here, I can put a nanowire here. Or just nanowire here. I know I need to couple, of course, make sure this photon can go in. I need to have the right impedance matching. And then nanowires here, and then I just give an example, not the real one. I don't know how to do it, right? I assume this is the nanowire, right? Variable resistor, and then I just put a voltage source. I don't know, something like this, and then once it has potential drop, then the voltage across here will change, right? Then I know that a photon has hit my here, so I measure one photon. Make sense? Yeah. Okay.
So this one doesn't require negative feedback, I guess? Like
You can. That is the circuit. Oh, of course you need to make it back, right? The critical current, so that you go back to superconducting state, then you can get do another measurement, right? You don't want to always in the the normal state, right? You need feedback. Here we're just talking about how it detects it. I think you need the same quenching circuit, something similar, but the design may be different. So we know how to measure. Why I say so much is about what? I'm done with the two well-characterized qubit. I also done with the measurement, right? And then, but we also need to know how to do the generation. So this is again not my expertise, but it's good to learn. I think maybe you guys are better than me. There's something called spontaneous parametric down conversion, right? So you need a nonlinear crystal. You have a pump laser, have a certain frequency, a high frequency. So this down conversion is going to generate two photons, one single photon. Okay, so that is the technique they have been using. And this is, I think even they can use in superconducting qubit, because do not forget, photons are just electromagnetic waves. So you can have the similar thing to do parametric down conversion in the superconducting qubit for some experiment. Okay, so then you get a signal here and what we call idler or herald photon. So basically this one is like, how do you know one photon is coming in some algorithm? You actually have two photons coming out together, they're entangled to each other. And then when you detect this herald one, then you know the other one is here, then you do the operation or do the detection. Okay. So this nothing special. All you can see is just I pump it up and then I get two photons with lower energy, right? So you can use to create the entangled photon because they're entangled, just like here. The laser beam come in through this nonlinear crystal. Then you will get these two photons in these two locations with this entanglement, either horizontal or vertical polarized as the qubit, right? Just, that's it. That's all I can tell you. And it's okay? Maybe the physics people know better. You can ask them after the class. So the last thing I want to say is the single qubit gate, right? And then we will finish the photonic. Very simple, very superficial discussion. I don't have much knowledge about this, but I think you can read it yourself. Photonic quantum computer. So how do we need to encode it, right? We have 0. I can say maybe how about horizontally polarized? And that is nothing special. I can call it 1, 0. I have 1, which is vertically polarized. And then I call it 0, 1. Okay? Now, we can look at the density matrix of it. This is how they like to treat it. Do you remember how to find the density matrix of a vector?
Probability of the
Yeah, just the upper product. Yes, yeah. And now I only look at the density matrix of H. Then it is 1, 0, 0, 0. And then that of 1 is 0, 0, 0, 1, right? This is what you learned before. Oh, yeah. And in general, so because of this, right, in general, the density matrix can be written as A, B, e to the I delta. You have not seen this before when we learned the density matrix, but this is just a transformation that we try to represent it in this form, which is nothing special. Of course, this equal to I plus gamma dot sigma, right? If you remember, yeah. Yeah, yeah. No, I'm just saying that this is not a dual rail encoding. I just encode it either horizontally or vertically polarized as 0 and 1. So that photon can be a linear combination of 0 and horizontal and vertical polarization. I don't know that well. Yeah, I cannot give you the pros and cons. But the dual rail, you can see that you need a special equipment or space, right? In the space, you have larger space. And another is that dual rail actually help to solve some of the, how to say, the detection error. Because if you get 0 photon in both paths, for example, you know that is an error, right? But if you this encoding, no matter you will collapse to something, or if you don't get photon, then or you don't get, I don't know. So they have an extra layer of protection already from the error. There's still error, but extra layer. That's the good thing about dual rail. Okay. Yeah. Well, yeah, then you need to the same. You still use that technique, but then you need to convert, just like what we did in spin to charge conversion, right? You just convert that when you detect something is horizontal or it is vertical. You use interference, right? Or use yeah, I think mostly interference to do that. Yeah, do some conversion. Okay, so in this case, right, we can say A equals to cosine square theta, and then B equals to sine theta cosine theta, and then delta equals to negative phi. When we map to the sphere, okay? They usually map this to the so-called Poincare sphere, which is pretty similar to the broad sphere. Okay, but that's just for the photonic guys. You still have X. I don't know why the Y is here, but anyway, you have the vertical polarization here, horizontal polarization here, and this is like 0, and this is like Y, like 1. Okay, so it's not North Pole and South Pole. Okay, because of this mapping, right? We won't go into details, but the point is that you will see that just from here, definitely A equal cosine square theta, so A must be less or equal to 1. And you can see that B, right, equal to sine theta, which is square root 1 minus cosine square theta, and then times cosine, theta, right? Which is equal to square root 1 minus A times square root A, right? So, which means it needs to be less than A times A minus 1. So just some number that it will be useful. I'm not going to go to this in depth because just some math, right? You know that it is math. Because I only have 1 minute, I still want to finish this part. So how do you do a single qubit gate? you pass through, this is one example, right? This is not integrator one, or you can do integrator one. You have a half waveguide plate, half wave plate. This is called half wave plate. And this is the quarter wave plate. It means the thickness is 1/4 of the wavelength. Okay, and unfortunately, all I want to tell you is that, yes, they prove that if the operation of this half wave plate is equal to this, cosine 2 theta, negative sine 2 theta, negative sine 2 theta, and then cosine 2 theta. So you can try to, for example, if I pass through this one by, this is the axis, theta 2. This is the major axis of this crystal. If I pass it by theta 2, I will be able to rotate my vector by 4 theta 2. Okay? And the quarter wave plate is like this, which is maybe meaningless to copy to you, but you can look at that paper. But let me just quickly copy. Negative 1 plus I sine theta cosine theta. And then negative 1 plus I sine theta cosine theta. And then 1 minus 1 plus I sine square theta. So meaningless to tell you this. But after all is that, how does it evolve? If you have a density matrix, for example, you pass through the halfway plate, theta 1, then it will be transformed to this density matrix. Right? You see that the whole thing is playing, is like, they formulate in the density matrix. It will be easier for you to look from density matrix how you transform one state to another state. Okay? So no insights, no nothing. I will actually just stop here for the photonic qubit. I have no knowledge. Okay? So next Monday, I will talk about the error correction a little bit and then just review for exam. Then we are done. I kind of done what I promised in the syllabus, although slow. Okay, any questions?
For the final, how similar to the base year? Or is like, are there going to be example questions or still be mostly math and logic?